All right, let's get into something that feels, well, completely backwards. We're about to uncover a hidden rule of nature, a secret that explains why sometimes the faster the air moves, the stronger it seems to pull, not push.
I mean, really think about it. When a huge gust of wind blows, you expect things to get shoved out of the way, right? But what if I told you that's not always what happens? Sometimes it's the total opposite.
I know, these things sound totally bizarre. A shower curtain that actually lunges inward when the water is running, two objects that move into a fast stream of air instead of being blown away by it. It just doesn't feel right. But these things really happen, and they're all clues to a much, much bigger idea.
So to really get to the bottom of this, we're not just going to talk about it. We're going to look at a few simple experiments that show this strange effect in action. Think of these as our first pieces of evidence in solving this whole mystery.
Okay, first up, here's our setup. We've got two really lightweight balls, just hanging from strings, minding their own business. Super simple.
Now, just for a second, what does your gut tell you? You got a powerful blast of air going right down the middle. Surely it's going to push them apart. That feels like the only logical answer.
But that's not what happens. They actually move toward each other, not apart, together. This is a huge clash between what we expect and what we see. And it's not a trick. It's our first major clue that our basic understanding of air pressure might be missing something really important.
All right, let's try another one. This time, we have a ball, and we're placing it inside a funnel. Then we're going to blow air upwards through the narrow end. Again, common sense would say that blast of air is going to shoot the ball out of the funnel like a tiny cannon. But instead, the ball just floats there. It's suspended, hovering in the air, basically defying gravity. The fast-moving air is somehow trapping it.
So, whether it's two balls getting cozy, a ball floating in a funnel, or even a piece of paper that lifts up when you blow over it, we keep seeing the same bizarre pattern. Fast-moving air is creating this unexpected pull. So the question is, what on earth is going on? To answer that question, we have to change how we're looking at the problem. Let's stop focusing on the objects for a minute, and instead let's look at what the air itself is doing. Okay, imagine water flowing through a big pipe that suddenly gets really narrow in the middle. The same amount of water still has to squeeze through that much smaller space. So what does it have to do? It's got to speed up. It's exactly like when 3 lanes of highway traffic merge down to 1. The cars have to go faster to keep things moving. This gives us our first rule. When a fluid gets squeezed, it speeds up.
And this is where a super smart scientist from the 18th century named Daniel Bernoulli comes into the picture. He had this brilliant idea that connected this change in speed to something even more important: pressure.
Let's think about that water speeding up. I mean, basic physics tells us that to make anything accelerate, you need a force, a push. In fluids like air and water, that push comes from pressure. So for the water to speed up right as it enters that narrow part, something has to be pushing it from behind, right? And this is the core of Bernoulli's incredible discovery. For that water to accelerate into the narrow section, the pressure in the wide part before the squeeze has to be higher than the pressure inside the squeeze. This pressure difference is what provides the push. And that leads us to his amazing principle. When the speed of a fluid goes up, its internal pressure goes down.
This is it. This is the whole secret. If you remember only one thing, make it this: faster flow equals lower pressure. This simple, beautiful rule is the key that unlocks all of those mysteries we just saw. All right, so now that we're armed with our new golden rule, let's go back and crack these cases. Suddenly, everything that seemed totally impossible is about to make perfect sense. Remember the 2 hanging balls? When we blow air between them, that air is moving fast. And according to our rule, fast air means low pressure. But what about the air on the outside of the balls? That air is just sitting there. It's slow, which means it has higher pressure. And that higher pressure on the outside literally pushes the balls together into the low pressure zone. They aren't being pulled, they're being pushed. And the ball in the funnel? It's the exact same idea. The air is forced to squeeze through that tiny gap between the ball and the funnel, so it speeds up like crazy. This creates a little pocket of low pressure around the top of the ball. Meanwhile, the normal, higher pressure of the air underneath the ball pushes up, holding it in place against gravity. And just like that, mystery solved. Now that we've cracked the code, you can see this isn't just about cool party tricks. The single principle is one of the most powerful and important concepts in all of engineering and physics. And once you know what to look for, you will start seeing it at work all around you.
In fact, if you've ever blown across the top of a straw that's in a drink and seen the liquid rise up, you've just used Bernoulli's principle. The fast air you create has low pressure, so the higher pressure on the surface of the drink pushes the liquid right up the straw. That simple action is the basis for everything from perfume bottles and paint sprayers to the carburetors that mix fuel and air in engines.
And don't ever underestimate the power of this pressure difference. If you can create low pressure inside a flimsy plastic bottle, the regular atmospheric pressure on the outside is so strong it can instantly crush the bottle flat. We're talking about an immense, invisible power.
And this is really the big picture. Bernoulli's principle is the reason airplanes can fly. It's what creates lift. It's how race cars generate downforce to hug the track. And yes, it's why your shower curtain mysteriously attacks you. It's a fundamental force of nature that we've harnessed to achieve some pretty incredible things.
So, at the end of the day, the secret is this. Fast-moving fluids do more than just push. They fundamentally change the pressure all around them. It's that controlled difference in pressure that allows us to generate forces strong enough to lift a 400-ton airplane off the ground, or gentle enough to pull two little ping-pong balls together. So now you're in on the secret. The next time you see a flag fluttering wildly in the wind, a piece of paper lift off a table, or you feel that shower curtain moving in, you'll know exactly what's going on. The only question is, where else are you going to spot it?